All right, everyone. Welcome to the first day of Capstone. We are not going to talk about that or announce your groups for another like 45 minutes. Instead, I will keep you in terrible suspense while talking to you about optimization. Sorry.
No, you're not.
No, I'm not. We had to spend like hours making the groups, so you get to spend another hour waiting for them. That seems fair, right? I think you'll be pretty happy with them. Most people ended up like objectively happy by the integer happiness scores that we created for all of you. All right, so let's talk about making things faster. So at some point in most technical interviews, you will have put up some answer on the board. You will have gone through the REACT steps. Yeah, you will, which means you will have code. That code will work, or you will have reasonably proven that that code works, and then the interviewer will say, "Can you make this faster?" To which it might be tempting to respond, "Well, if I could have, I would have, but I guess you want it to be faster now." So that's the time to kind of reconsider your approach. Mostly, the interviewer is not asking about, like, oh, could you use a while loop instead of a for each, because, like, a decrementing while loop is, like, slightly faster. It is slightly faster, and that's nice, but those kinds of micro-optimizations are not usually what they're after. What they're usually after is an improvement in the big O, either runtime or space complexity. Usually time complexity is what we care about. Sometimes we care about space complexity. Sometimes your interviewer will say, like, okay, but can you do this without taking all this extra space? Let's talk about time first. So here I have my answer to the Fibonacci question, which is like write a function that returns the Fibonacci sequence. It's recursive, it's beautiful, and when I run it for the number 1, it works well. It like runs in 1 millisecond. Oh, there we go. When I run it for 2, nothing happened. Oh, weird. Sure, 1 second. I'm gonna restart Node1.
Why are you using npx for Node1?
Because I don't install anything globally, really.
Really?
Yeah. Because you're constantly switching node versions, and who knows what version of that thing you have installed in the node version, and the package that you're in specifies, and I should have it locally installed in this package, but I don't, because I don't know why. Okay, there we go. So when I run it on 2, I get the correct answer, and it takes 2 milliseconds. If I do 10, 3 milliseconds. So this is looking pretty good so far. If I do 20, still looking good. If I do 30, 18, I'd expect this to be doing worse by now. 50, oh shit. Okay, 50 is not so good. How about 40? Okay, so 30 took 20 milliseconds, 40 takes 10 times as long, well, like, about 50, wait, 10 times as long? No, 5 times as long. 35. So somewhere between 30 and 40, this, like, blows up. And if I try and do, like, 41, I bet it's going to be this little catastrophe. Yeah, so 41 is almost twice as bad as 40. What does this look like? I could be plotting these. So after this initial period of like, oh, things appear pretty much fine, like 1 and 2 and 3 and 4 all seem to take about the same amount of time. Now, every time so this took like 7 seconds, let's try doing 44. I'm guessing we've got about 14 seconds. 5 Mississippi, 6 Mississippi, 7. Okay, 11 seconds. What does this look like? Yeah.
It looks like you're hitting a lot of constant stuff, which is why we don't see the scaling until we hit 40. But now you're running into some sort of geometric scaling.
Yeah, so what is, like, analytically, what is the big O of this function?
Exponential.
Yeah, and which exponential in particular? There's a couple of bounds you could get.
To the x, I think.
Yeah. Sorry, what did you say? Q? 2. Yeah, it's 2 to the n. Do you have, like, reasoning behind that? Other than it kind of just looked like it was doubling? What's that?
Mostly that it's doubling every time we use the button.
Yeah, so empirical reasoning is pretty good. We can also notice that every call to fib results in 2 more calls to fib, which sounds kind of like 2 to the n. In fact, there's a tight bound on the big O of this, which is phi to the n plus 1, where phi is the golden ratio. It's like, I think, 1 over the square root of 5. Does that sound right? In any case, that is very closely related to the closed form approximation of the Fibonacci sequence, and there's a whole proof that that is the tight bound from MIT if you're interested in it. It's not too hairy, but it is a little bit odd. But anyway, it's like in the neighborhood of 2 to the n, which is, you know, a catastrophe. For this reason, right? Like, everything looks fine, and then you just hit this wall, which is what exponential scaling feels like. It was scaling exponentially even below that, but what was happening was that this timer, the terrible timer I have by using date.now, is not very accurate. It gives us milliseconds, but it's unlikely to even be accurate to within milliseconds. And then there's also some, like, constant time noise from the fact that, like, calling this function requires something. Console log takes some amount of time because the output buffer has to flush, and there's all sorts of things that can dwarf the cost of merely a few million function calls. Maybe a few thousand function calls at the low end. Okay, so how do we make this better? Yeah.
You can use memoization.
Yeah, oh, great answer.
Can you repeat the
Yeah, so the question was how to make it better. One answer is memoization. So with memoization, we say, hey, we notice, first of all, that most of this work is repeated. So when I'm computing fib of n, I'm computing fib of n minus 1 and n minus 2. And then when I compute fib of n minus 1, I'm computing fib of n minus 2 and n minus 3, keeping the same n here, which means that I'm computing fib of n minus 2 twice. And that just gets worse and worse and worse until I'm actually computing fib of 1, like, 2 to the n times, I think, or something around that bad. So we can bail early. And there's a few ways of bailing early. I'm going to say, I'm going to wrap our fib function in another function. And this one is going to first say if n in memo, return memo of n. Otherwise, it's going to put the return value into the memo and then return.
Can you talk about the in statement you just used for n in memo? What is that doing?
Oh, this is checking to see if the key n is within memo. We could use a set as well, if we wanted to use a set. It doesn't really matter here. So now, our elapsed time is 2 milliseconds, and it's just going to keep getting better, like 80, great, 90, 500, yeah.
What?
What? What? Why did that help so much?
Yeah.
Because we're eliminating a huge amount of repeated work. So we're basically eliminating the extra call that led to this being 2 to the n, so now it's just n. Because now every time, this fib of n minus 2 is already computed, it's just a hash lookup. Always. Another way you will sometimes see this written, if I was feeling really crazy, I might write it like this, is to say fib takes n and returns fib of n, oh, sorry, if n is in fib, then fib of n, otherwise 1 plus fib of n minus 2, this is the form that you write it in if you want nobody to understand your code, but it means the same thing. It means almost the same thing. This is actually, this has a slightly different implication than this. Can anyone see what it is?
Line 13, you check to see if n is inside of a function called fib.
Sorry, line 13?
Yeah.
Yeah, so here we're using the function object itself as a memo, which is weird but cool, I think. If after doing this we log fib, the function itself, we'll see that the function object has all of this crap in it. It's a function, and it has all of these key value pairs. So that's kind of cool. It's also maybe problematic in that we have this memo that's sitting on the function and growing forever. Like, whenever anyone computes a Fibonacci number, it fills in this cache. On the other hand, it means that subsequent calls will be extremely fast. Like, they'll just be O of 1 lookups if you've already computed it. So you might prefer to do that if you know that you'll be calling this function a lot and you don't really care about the space that the memo takes up.
Why is the space storing it on the object, on the function object, different than storing it in a JS object?
So storing it here, every time we call fib, so this is like, let me just ambiguate these. This is inner fib. Let's comment that out. So here, every time we call this function, we're going to have a new memo. So this memo only applies to this single invocation of fib of n. So we can see this behavior because, first of all, if we look at the function object, it's just the function. Second of all, if we compute this twice, oh crap. What? Damn it. If we compute this twice, we'll learn that V8's optimization is kicked in, and so we're screwed out of a great example. Damn it. So, part of how V8's optimizing compiler works is that after you call a function a whole bunch, it examines it and considers it for tighter optimization, which means that if you do this thing, this sort of thing, and you call the same function twice, it will you will sometimes get a more optimized version the second time, which is great, but also means that this demo is not showing what I wanted it to show, which is that this version, you have to do this loop every single time, whereas in this version, if you have ever previously in the lifespan of this program computed a given n Fibonacci digit, you will hit this branch, and you will just return it immediately. But I can't show you that because V8 is too smart for me. There's probably some like prevent. Oh, actually, maybe if I let's try this. Try. Damn it. There used to be a lot of nice ways to prevent, well, terrible ways to prevent V8 from optimizing a function. Like any function with the try finally or try catch could not be optimized.
What does finally do?
Finally says run this block of code after this has run no matter what. So like if I put a console log here, I am exiting. It runs, even though I've returned here. Oh yeah, that's a nice thing to know, especially in the context of async await. Do a bunch of stuff and then always clean up in this way, or always like do something at the end is what try finally is for. You can also catch. This is the like full form of a try catch construct. Just learning all kinds of things today. Okay, so I can't really demonstrate this, so you just have to trust me that that this is retaining the memo and this one isn't, and that that has some performance impact, even if we can't see it on this example. Okay, other questions about this? Or if we would rather nobody understand our code. One, I will say this has one. I'm making fun of myself really for writing code that's like dense with ternaries and operators and not necessarily that readable. But it is very short, which can be a boon on a whiteboard. So that's something I think about at least when whiteboarding is not necessarily like I'll tend to avoid while loops or for loops if I can get away with a map or a reduce because those tend to be a bit shorter and a little bit more. Like a little bit easier to read when I write them. And then if they're like, what are the performance impacts of this versus a loop? I can be like, well, the loop is a bit faster, but do you care? Probably not. Did you want to read a while loop? No, you didn't. Do you like how I draw curly braces that much? No, nobody does. Okay, I have one other example, if there are no more questions about this one. Okay, cool. Let's consider here I'm gonna open some. Okay, so let's consider this problem and let's just work it right up here. So the problem is given a target number, find a pair of numbers in, given a target number and an array, find a pair of numbers in the array that sum to the target. Okay, so how might we approach this? Have you done this problem yet? You have done this problem?
Code Wars.
You oh, okay. If you've done it and found the most optimal solution, shh for a second. What's like a naive approach? Imagine that like I'm a Google interviewer staring you down, and yeah.
The first thing I would do is I would eliminate any values in the array that is too high. You know, assuming that the array has value that's larger than the number I'm reaching for.
So this is saying like filter out everything in the haystack where x is greater than target, but there can be negative numbers. So you might need that negativity or that positivity. to counter the negativity, to find exactly the right balance. Yeah.
A naive way would be to look at one element and look through all of the other elements in the array and keep doing that for each element.
Yeah, so we could say that for, let's see, I just want to say find, right? So find an element in the array, xi, such that there's another element in the array, yj, where, did I say that, I think I shouldn't be j, so they can't be the same number, and x plus y is target. And then, what the hell does find return?
The actual element.
The actual element? Okay, fine. We'll say that's fine. Except I want the two indices.
You can find index.
Oh, find index. Thank you.
I think that's what
Yeah, great. Thanks. Okay, and then let's try this on, I want numbers that sum to 6 in 1, 7, 2, minus 1, 3. And I should log that. And also, I should probably... Oh, sorry, this is going to get a index. And this is just, so this is returning the first index, which is correct, I think, because we want 7 and we want minus 1. I just need to get this out of there. Should I just be writing while loops? I should probably just be writing while loops, shouldn't I? Damn it. I just said I wouldn't write while loops. Whatever. Haystack.length while I goes to 0. I guess. Yeah. While j goes to 0, if I isn't j and haystack of I plus haystack of j equals the target, then return ij. This is what I get for trying to use array methods. While loops all the way. I take it all back.
We put return the index or we put the return the value?
I'm going to say the index. Because the values, if you lose the index, then you can't recover it, it's an OFN operation to recover it. If you lose the value, then it's an OF1 operation to recover it. So I'm saying return the index. So this came up with 3 and 1, 1 and 0, 1, 2, 3. Correct. Great. What's the big O of this? N squared. That's unfortunate. Could we do better? How could we do better? Yeah.
The other number would just be equal to target minus that number. So you can check if that exists inside the haystack just by include. Maybe that's
That include is OFN.
You can store all the values you've seen before, so you can do an easy lookup for the pair that has a.
Yeah, so when I look at a number, I could be like, hey, does this have a mate somewhere? Which maybe means we can just scan the array and find, scan the array into like a dictionary and store its sorry, I can scan the array into a dictionary, which is an O of n operation, and then I can look for the mate of each number in the dictionary, which is another O of n operation. So I get O of n in time and O of n in space, which is usually a reasonable trade-off. So let's say that numbers is my, so this will be a mapping of numbers, I guess it's number to index, and first I'll scan the, first fill numbers. So I'm going to say that numbers of haystack of I equals I. It's like, and then next find mates. So as soon as I find a number in here where, let's see, if numbers of target minus I, so this is saying if there's something in numbers where, sorry, haystack of I. If there's something in numbers where my current position plus that number equals the target, then, okay, and numbers of target minus haystack of I is an I, which actually I'm not sure we want that criteria, but we've had it before, so we'll keep it. Then return I and numbers of target minus haystack of I. I'm going to compute this beforehand because that's kind of ridiculous. We're going to call this our mate. So if we find our mate and we are not our own mate, then return ourselves and our mate. That's way more legible. Identifier I has already been declared. 3-7. Right. Not our mate, but the index of our mate. I think I should call this indices. That looks right, yes? Yes. It's not returning them in the same order. We never said that we care about the order, so that's fine. I guess here we should return something else, but undefined is fine. Okay, so what's the big O of this? We kind of said it, but let's look at it again. Yeah, it's O of n, because we do an O of n thing, and then we do another O of n thing, so 2 O of n is also O of n. And then what's its space complexity? Also O of n, because we build this index that's the same size as the array. That's often fun. It's often totally reasonable to have, to choose to take up space in order to save on time. Space is generally considered cheaper, and especially like in actual production applications, that's usually what we do. Like Google, in order to get instant search working, basically just has the entire internet in memory so that they can do hash lookups on it. They're not quite hash lookups, but they're like tree hash lookups, which is very fast, also very expensive, but they're very rich, so it's fine. It's all fine. But in this case, we can actually do even better, and I think we can eliminate this index. Thoughts on how? Yeah?
Sort the array and then use pointers such that if you're like too low, you can move one, and if you're too high, then you can move another. And then if you get to the point where the pointers are past each other, then you know you're done.
Oh, interesting. Maybe.
What did she say?
So, she said sort the array, and then use pointers on either end of the array. So if you're too high, you move down the high one. And if you're too low, you move up the low one. But what if you were supposed to move up the high one for being too low?
Isn't it like once you start at either end, you shouldn't ever have to go back?
You shouldn't. I agree. But I'm not sure how you know which pointer to move.
If the sum of the two values is too great.
If it's too great, there's two options, though. You could move down the low pointer, which will get you to a more negative number, or you could move up the high pointer, which will get you more positivity in your life.
But if you start already high, you would already tried that, wouldn't you have?
Will you necessarily have tried that?
And if you're already starting from as what she's saying, if you started from each end, you wouldn't go backwards. What you're saying is move up. That's going backwards, isn't it? You should have already been there.
Oh, I see. Yeah. So you only ever advance one of them.
Right. You should never go backwards by
And you only advance. Yeah, I'll take it. That sounds great. Oh man, now I get to write this. So let's try it out. Yeah, that sounds right. All right, so we've got let I equals 0. I feel like these should have different names. Let low equals 0, high equals haystack dot length minus 1, and then while low isn't high, sorry, while low is less than high. Yeah. What do we do if haystack of low plus, what's that? Oh, thank you. Oh, yeah, good point. Thank you. Wait, I need to store the indices after I've sorted?
Yeah, because sorting will...
Good point, good point. Wait, that means...
What do you think?
That means that I can't do it if I want to return the indices and have OF1 space. Because I need to retain that mapping.
I think you should start with the sorted array.
Yeah, that's a good point. The haystack must be sorted. Yeah. Now we're done. Yeah.
I got you.
But you could do for O1 space, you could sort the array and then step through it and search for something that would sum to our target. Because there's only one possible value to sum to the target if you already have one value from the thing. So you could do a binary search for that element.
Right. So that would give me O of n log n, I think.
Yeah.
But then, wait, I still don't get my indices back. I think, actually, I can't do this if I'm returning indices, which means I kind of screwed up by making that the contract.
Wait, I think you can do it.
I can?
So
I'm excited.
if in the process of sorting the array, you're in fact creating a new array of objects, which are the value paired with the index from the original array.
But aren't those taking up space?
Yes, but it's only constant space. Or it's only n space.
Right, but we're trying to do it in OF1 space.
Oh, okay.
Right. We have it in OFN space, OFN time. Yeah. No, but I actually think, like, I screwed up by saying we're going to return the indices, because I think if you just return the numbers, which now is what we're going to do, then we just have to sort the thing. So haystack, that's...
Slice the haystack and copy it, and then just return the indices from the original array after you find.
Wait, sorry, say that again?
Like, keep the original haystack as is, but create... Yeah.
Yeah. I think we have to retain the mapping if if we're committed to returning indexes. But we're not. I made that commitment. Now I can break it. I made the commitment only 10 minutes ago. There's a 10-minute rule in programming where you don't have to keep your promises for more than 10 minutes. In JavaScript, it's 2.
You talk about JavaScript promises?
Yeah, I'm sorry. Can you explain why this wouldn't work if you copy the array?
Because I copy the array.
That's it. Because that's O of n.
That's O of n space. It's another copy of the array.
To sort it though?
No, to copy the array is O of n space.
Alright.
We're just no, we're just fucked. We just have to not. we can't do it in O of 1 space if we need the mapping. I think it's the problem. Okay, so if we've found it, then we're going to return here. I'm going to call these. I'm going to change my mind here and say this is L, this is H, while L is less than H. If so, low is haystack of L, high is haystack of H. If L plus H, or if low plus high is the target, return low high. If here. If sum is less than the target, we're going to move the low up 1. Does it matter?
Yeah, you want to move the high down. Moving the low up will increase this one.
Oh, right. It does matter. And if it's greater than the target, we'll move the low up.
What's that continue statement?
This continue statement?
Mm-hmm.
It says don't. It says go to the next while. So basically, don't do this, which is unnecessary, strictly speaking, because these are mutually exclusive branches.
Actually, I think these are reversed.
Yeah, these are reverse. If sum is greater than the target, then move the high down. If it's less than the target, then move the low up. Hey, cool. So this is, unfortunately we had to change the contract, which slightly impedes the pedagogical value of this, but we're doing a very similar thing here to what we were doing in this version, only we're being a little bit more clever about how we evaluate these, like when we evaluate these comparisons, so that once we get to a certain point, we know that we've evaluated all of the subproblems that come from like the other parts of the array. So basically, this is a dynamic programming solution to this problem using ratcheting. Like at each iteration of the while loop, we have a state which we know is the current best state, or in this case, a state where we have eliminated all possibilities of the parts of the array that we have already seen. Yeah.
What if there more than one pair of the sum exists?
Oh, then you just have to return one of them.
So if the sorting, it can be different value will return than not sorting.
Yeah, sure. Yeah, you might get a different answer, but you just have to return a valid answer in this case. In other problems, there might be more specificity. So did this just pop into your head?
No.
Okay.
It was like heard about this problem before, and that was like this. And I think it was a problem where you already had a sorted array. So
Right.
we were going through the other solution. I was thinking about it, but then Yeah, and it didn't like dawn on me that keeping track of the indices would be an issue.
Yeah, but usually these problems are phrased as return the actual thing, not return the index. I just got too clever for my own good when deciding this early on. But that's also okay. Like in an actual interview context, you can probably revise your contract if you imposed it upon yourself. Like if early on you're like, I want to return the indices, and the interviewer is like, fine. Now you're like, oh, I don't want to do that anymore. Also probably fine. You just have to, as always, communicate these things. Okay. We are close to time. Any questions? Okay, so this week's reactives are going to be all about optimizations. There will be usually a sort of naive approach, which please don't go crazy trying to find the most optimized approach first, because that's a really good way to stand there at the whiteboard being like, I see this like n squared approach, but I am pretty sure that that's not it. So I'm going to like drive myself crazy trying to come up with a better approach. Instead, like go for at least like lay out a naive approach, and it'll help your thinking, and also it'll demonstrate that like you can do something and you can think through a problem. The point again is to think through a problem in front of an interviewer so that they can understand your thought process and help guide you through the problem. Yeah.
Do you have any tips on how to, like, what process to use, like thought process, I guess, to arrive at these optimizations? Like, I'm not sure I'd ever get either.
Yeah, so the last one is definitely tricky. You saw, I had to think about it. This does kind of seem like a problem where there's a ratcheting approach that can work, because you have, especially if you sort it first, because how do I articulate that intuition? Because you're looking for something that you can determine locally, or that you can determine locally given some previous state. So other types of problems that fit into this are like find the maximum difference between two numbers in this array, where even without like thinking about the whole approach, you can sort of see like there's some way to scan over the array and remember where you've been, and the best thing you've seen, and then return the best thing you've seen at the end of the array. So that, like, putting yourself in that perspective of like, I am the enzyme scanning this DNA and I'm remembering some state, that is the thing I will eventually return, can help guide you towards coming up with like a scanning solution. And then also considering pre-processing steps. So this doesn't work on an unsorted array, but sorting is quite cheap. Sorting is n log n. So if that's an acceptable runtime, which it always is, basically, then you can sort to pre-process and then do some optimization on it. This is usually easier to get to, some solution which trades off space for time, and is usually a good thing to get to. So the trade-off here is that we have to keep track of this indices block, which in this case keeps track of the indexes, but in other versions of this problem keeps track of the difference between the number and the target. But either way, if you can either memoize or keep track of values you've seen before so you don't have to recompute them, you can trade off space for time, and that's usually a worthy trade-off. So this is usually easier to do because you can say like, hey, when am I recomputing something that I've already recomputed? Fibonacci, either memoizing it or doing the crazy memoization of it, or the ratcheted version of Fibonacci is the iterative solution, which is actually definitely the fastest. So these are all kind of incremental stages of optimization. The first stage is to be like, where can I avoid duplicating work by saving what I've already done in a memo or in a cache? And then the second step is, when can I just throw things away from the cache? And in fact, if you can get it down so that at every step of the loop, there's only one thing that has to be in the cache, then you have a ratcheting solution. And this week, you get to practice. All right. Any other questions? All right, take a little break. Gabe and I and your fellows are going to confer, and then we will have a grand announcement of your capstone teams. Yeah. Hi. Yeah.
So how would a closed form solution of the Fibonacci numbers, how would that compare in like time complexity?
Oh, closed form would be great. Oh, fun. Is there an actual closed form to get the exact Fibonacci number?
I think there is.
Okay.
I was trying to, but for some reason I was looking it up on Stack Overflow because it first of all, when I was trying to implement it, it wasn't working in JavaScript. There was some like rounding errors.
Yeah.
Yeah, but on Stack Overflow, people were saying that it's actually not like one. It's like log of n because of input size. It's called like Benet's formula.
I don't care where you drive me to. I didn't intend to drive my car because I have to leave today. To go to Jersey, so I wouldn't be able to do that. Anyway, the room's brother got married Sunday. I'm one of my good friends. I will drive you now. I was great. I gave him my keys. And then he said, I'm not driving your car, I'm driving your car. I was like, no, like.
Log of n, that doesn't sound right.
I said, you are either.
Like I looked up Fibonacci in constant time.
I'll drive you tomorrow. Anyways,
given arbitrary large
given
inputs,
arbitrary large inputs.
Yeah, simply reading in n takes O of log n. So in that sense,
yeah. No,
but it's constant otherwise.
I would call it constant if like. It doesn't take n. Well, yeah, it takes log n. Sure. Very, very rarely do we talk about that, though.
Okay.
I would say.
Cool.
But yeah, reading n takes log n because it's n digits.
Right. But if it's the closed formula that's like plug and chug, so it's just linear time.
Mm-hmm. No, it's just constant.
Yeah,
constant. Yeah.
Just want to remind you, I can't hear any of the students, so when they're talking to you and all you do is respond to the answer, I'm not hearing the benefit of what they said.
Sorry.
So it's like I want to hear the back and forth so I can think, oh, if I have that thought, then this is why I should not go down that path. I can't hear what they're saying, I get to hear your responses to them.
I'm sorry.
So I just want to remind you.
If you have any questions about what people were asking.
Well, I do. The problem is, when they spend 2 minutes talking about it, I feel more reluctant to actually repeat it because I have no idea if it was worthy or anything like that. But
yeah.
Just wanted to remind you.
I can put one on the.
And I pissed off one of my friends.